Hello and welcome back. In this video we'll talk about neural networks and deep learning, and we'll introduce the concept of neural networks and network training. Let's start with a crude analogy to see where this term neural network comes from. So in a very simplified pictures, we can describe our brain as about roughly 90 billion or 9 to 10 to the 10 brain cells. These are also called neurons, and each neuron is connected to thousands of other neurons. So that means, in this very simple picture, that a memory is built by building connection patterns between different neurons. So that means that our memories and our thinking processes are not stored in the way neurons are in our DNA, but they are stored in the connection patterns between neurons. Just to stress again, this is of course a very simplified picture. But it serves as a ground of how artificial neurons are built. So how does a single neuron work? Even more simplified, right? So we have connections from all the other neurons. These are like thousands of connections, and they come via these dendrites into the nucleus of our neuron. And then there's this axon. This is essentially the output of the biological neuron that connects them to thousands of other brain cells. Now, how do we do this? Essentially, the dendrites collect the signal from all those thousands of other neurons and combine them, and then the axon decides to some extent if this neuron, we say, fires or not, or if an output is produced. And you can see that there is an action potential, right? So if the input exceeds some sort of threshold, then this neuron is said to be fired and produces an output. And because we have so many neurons and so many different connections, this is then how we form memories. Again, this is very simplified. Let's do this a bit more abstract, and this brings us to how artificial neural networks are built. So we have n inputs. We take the weighted sum, right? So we need to talk about those weights, of course. And each variable is one connection to other artificial neurons, and then we determine the output, just as we've seen with the complex curve with the action potential, and we call this the activation function, and then we connect to some other neurons. So what are these activation functions? They are key ingredients of neural networks, and they decide on how to modify the weighted sum that we receive as input and produce an output. One key feature is that these functions are nonlinear, and this enables neural networks to learn complex tasks. The traditional ones are sigmoid or tangent superbolicus, and they work well for small networks. You can see on the top right and in the middle these activation functions, and the modern ones like ReLU and similar, they are piecewise linear, and they're more used for deep learning. They have been invented to essentially avoid the vanishing gradient problem that will happen with these more traditional ones like sigmoid and tangent superbolicus for large networks. So how do we then build from these neurons neural networks, right? So the key questions here is, how do we arrange these artificial neurons now that we have defined them? That means, like, how many do we have and how do we connect them? And what we then also need to talk about is, how do we train this? So we need to decide on an activation function, and we need some sort of recipe how to change those weights, because as you remember on the previous slide, the weights are what is received, how we transform the received input from the other neurons. So the simplest thing you can do is a feed-forward network, and this is also where all these neural networks started. You have some input layer, one or more intermediate layer, and an output layer here in yellow, green, and blue. And essentially, it's of course a bit crude, but essentially if we go from simple networks to deep learning, is we have more everything, more layers, more nodes, more connections. Let's stick with a feed-forward network to understand a bit more how such a training works. So let's have a very simple setup. We have the input nodes. These are our variables. Let's keep it simple and think about tabular data. So we have variables, one variable per node and some values. Let's have some, only one maybe in this example, hidden layer with n intermediate nodes and one output node. For example, if we would do a binary classification, that would be enough. Feed forward then means information flows from input to output, or from left to right in this example, right? We forward it from the input to the output, and this is sort of the traditional setup pre-12 2012 or so, I would say. So this is what now would be called shallow networks, but this is what was state of the art about 10-15 years ago. How do we train them? Well, we've decided on the topology. That means the number of input nodes, the number of hidden nodes, the number of output nodes, and how do we connect them? Like in feed-forward, we connected each to each, layer by layer, but of course we could also have different arrangements. And we need to initialize the weights, right? So for example, we could just use them according to a Gaussian distributed random number or a uniform random number, and mostly these days we use the He and Gloro initialization because they're optimized for deep learning. We also need a cost function, because if we make a prediction, we need some sort of metric that defines how good our prediction is and assigns a number between the true label and our prediction. Typically what's used these days is a cross entropy for classification and residual sum of squares for regression problems. Right, and now we need a method to adapt the weights, and by adapting the weights means we want to reduce our cost function. That means we want to bring our prediction closer to the true labels that we have in our data. The two main methods, backpropagation and attention. I will talk about backpropagation first. How does backpropagation work? The main idea is that we calculate our prediction from the current weights. So if we haven't trained the network yet, we start with a random initialization so we can produce such a prediction. Now we compare this prediction to our true labels. This is why we need the loss function, right? So we have this E or cost function or loss function, the error, and that assigns a number between the prediction and the true label. Now we need some sort of way to change the weights to reduce the value of this cost function. So we propagate now the newly calculated weights, or rather the weight change, throughout the network. And the way it works is that we have a forward pass, so we calculate our prediction, and in the backward pass we work backwards to calculate the change of weights. Let's look a bit in more detail. This is then called gradient descent. So we need to determine the slope of a cost function with respect to the weights. So we want to go in the direction of the largest change. That means we want to make the change of the weights such that if we adopt this change throughout the network, the cost function will be smaller next time. Essentially, we can imagine we sit on top of a large hill and we want to find the valley where the prediction matches the true label best. More formally on the right, so the variation of the weights is the partial derivative of the cost function with respect to the weights and some learning rate alpha. Let's go through it step by step. For any neuron, we can define the output of this neuron as with O of j. So remember from the previous setup that we had, we have the sum of weights, the transfer function, and the output. So the x is the input, the O is the output. More mathematically, we have the output is the transfer function, S, of our sum of weights. Now, why do we need to start in the output layer? Because in the output layer, we can compare the output, this is our actual prediction, with the true label, right? We can't do this directly for the intermediate layers. So we need to propagate all of this, and the cost function doesn't explicitly depend on the weights, right? We can see where the weights enter because the output depends on the transfer function of the weighted sum. So it's not a direct relationship, but we can use the chain rule repeatedly. So we start in the output layer because here we know the true label and the prediction, and then work backwards to the input layer, right? And we can use the chain rule because then the derivative with respect to the weight is the derivative with respect to the output with the weighted sum, and the weighted sum with respect to the weights. And then we end up with the weights. So in the output layer, we know y and y hat, the true label and the prediction. And in the output layer, the prediction is also the output of the output neuron, right? So here we can calculate the cost function. So for example, we can take the residual sum of squares and then apply the chain rule repeatedly. Right. The second part of the derivative is just the derivative of the transfer function. In the modern ones, like ReLU, these are piecewise linear, so it's simple because then it's two constants. in sigmoid and tangent hyperbolicus, you can also do this analytically. Right, and then you have the weighted sum, and this then directly is directly related, and we can build the derivative with respect to the weights, and this is the input to this respective node. Right, so we've done now the output layer, and now we need to go back, because now we have the output of the output layer propagated to the next layer. Then now we know the output and the input of the intermediate layers, and so on. We've previously talked about the vanishing gradient problem, and that was in the traditional transfer functions like tangent hyperbolicus, right? We needed to derive the derivative in the backpropagation. This is we've just seen, right? The second part of the derivative was the derivative of the transfer function. Now with the traditional ones, you can see what happens here. If we take the sigmoid or the tangent hyperbolicus, the derivative looks like this. And this is 0 almost everywhere, apart from a very small region in the middle. Now this was not much of a problem in the shallow networks, where we only had maybe one intermediate layer, so all of this was quite simple. But if we have now many layers, like maybe for tens or hundreds of those, and you can see how this propagation of the weights, this gradient, becomes a problem, because if the transfer function, or if particularly the derivative of the transfer function, is 0 most of the time, then it will sort of start at the back, but then taper off and nothing will happen anymore. And that led to the development of linear rectifiers and its variants, because they don't have this vanishing gradient problem. You also remember that we introduced this learning rate, right? Here is just a brief recap, the parameter alpha, and that determines the step size in our gradient descent. Now we have a rule based on the chain rule, how to change the weights, right? And we want to do this proportional to the gradient, and we need to take care on how fast we want to propagate this weight change, because if our learning rate is too small, right, our learning will probably converge, but very, very slowly. It's illustrated here with a simple parabola. Of course, in this ideal case, we would know how to get to the minimum in one step. But since this cost function is a very complex one, typically has lots of valleys and cliffs and so on, and we can't do this in one step, we need to do it iteratively. So if we have a very small learning rate, we would converge very slowly. However, if we make the learning rate too large, the whole thing becomes unstable, because then we cannot evaluate the details of the gradient. You can see this with a small illustration on the right, and it might even happen that you don't reach the minimum, but you hop out again because you don't sort of see that there's a better value, and then you move on to a different area. How do you deal with that in practice? It's best to choose an adaptive learning rate scheme, so that you have a large learning rate in the beginning, and then reduce this if you're closer to convergence, or you can also do what's called cyclic learning rate schedules or annealing learning rate schedules. You change between large and small learning rate. That also has the advantage that you avoid getting stuck in local minimum. We've stressed before that building network means we have a nonlinear activation function. So let's discuss a little bit why that is so important. And there's on TensorFlow Playground, there's a nice illustration of how we can do this. So you can build a very simple neural network. Let's take two input variables, one neuron in the middle layer and the output, and start with a linear function. And you can see with this very simple data set, you have two blobs, and you can draw a straight line in between them and separate the yellowish from the blue one. And this very simple network learns this perfectly very quickly, because it's very simple to do, and you can do it by hand by drawing a single line. Now let's move on to a nonlinear case. By hand it would also be quite simple for us humans to do that. Now we have just 4 squares, right? But the key point is it's nonlinear in the sense that we can't draw a single line that separates the blue from the orange. If we try this, the network doesn't learn this. Okay, let's make the network more complex. Many more layers, many more neurons, and we can see it doesn't work. What we could do is now use our expert knowledge. And we can see that if we introduce a new variable that describes the particular behavior of the data points, then the network learns it even with a linear activation function. So if we have, as we say, good domain knowledge and we have human experts who know how to build such good features, we can use the machine learning algorithm to optimally combine those features. However, maybe we don't. Or we want to make use of the capabilities of neural networks, and now we switch to a nonlinear activation function. And you can see that even if we use those few two variables that don't capture the domain knowledge we might have about our input data, but by using a nonlinear relationship, the network is able to learn this perfectly again. When we train networks, let's talk about overtraining. Right? As training progresses, the cost function gets smaller and smaller, but of course we need to think about if we're just learning statistical fluctuations. Right? In overtraining, a network starts to learn the noise that are inherent to our data. So we need a test sample to check if what the network has learned is actually part of the features of the data set that we want to learn, or if it's really random noise. How can we do this? There are several methods. We could compare test and training data and use what's called early stopping and stop at the training at the minimum of the test error. This is very simple to do. We could also add some metrics, regularization techniques to it. It's called weight decay. So we add a penalty to the cost function, maybe the L1 or the L2 norm. That forces the network to have small weights, and small weights means it's getting a small network and doesn't learn so complex representations. That means the network actively needs to decide, shall we say, if it should learn a particular connection or not. Or we can have a pruning scheme where we remove connections with small weights in the end. One of those approaches is called dropout. It randomly drops nodes and connections during training. So that means that during training the network is sort of sparse. That means we have many small networks because at each iteration a different combination of node and connections will be dropped. Of course, when we do inference, we need to apply a correction to take this into account, right? But essentially it means instead of taking a big large network, using dropout, we take an ensemble of many small networks. So let's finish our introduction to neural networks and deep learning with what's called the bitter lesson from Richard Sutton. I'll just read it out. Researchers seek to leverage the human knowledge of the domain, but the only thing that matters in the long run is the leveraging of computation. Right? What he means by that is what we've seen in the evolution of deep learning in the past is that, of course, we as humans are invested in the problems and the challenges that we meet, and we want to contribute that. And in classical machine we did that in the sense that we built features that uses our expertise. But with the rise of deep learning, what we've seen in many application areas is that if you have enough data and compute power, and of course these are two big ifs, then neural networks and deep learning in particular are able to sort of learn from the raw data directly in the same performance level or even better than humans could do it.